All right, great. So we're moving toward the end. Also is a very important topic. So let's just do a little bit, in a relaxing mode, and I will do it also a little entertaining so that you don't feel, too tired toward the end. So yes, as you see my screen, right? So we're coming to the important topic. We're going to talk about numbers. I'll start with about number representation by posting a gesture here. Can you see me? Do you recognize me? Nobody? Maybe a little far away. Maybe Giuseppe, if you do it, people can recognize you. Because Giuseppe is from Italy.
He's a guy. Yeah, he's a guy from Mediterranean country, very old mathematician.
It's a mathematical celebrity who has been granted as the father of numbers. Is a Pythagoras. No, we know the Pythagoras algorithm. He has the school, talk a lot of things about numbers. But actually, history dated back even before his time. Back into the ancient Babylonians, they already have their own number system, but their number is different from ours. Our system on daily life, we use decimal, so-called decimal system. But there is a sexier. It's called a sexagesimal. And their system, I mean, Giuseppe, can you explain a bit what is a sexagesimal means?
Yes, so this is a Greek word coming from Greek ancient terminology. So sex means 6, and then the age stay for 60. And indeed, like Longzhu is going to explain, it's based on the 60 unit, let's say.
Yeah.
Okay.
Thanks so much, Giuseppe. Yeah. So instead of 10, so they have this value of placement that's done by every 60. So in their system, they have primarily used 2 symbols. One is a triangle upside down. The other one is like looking like a small less than symbol in mathematics. They represent respectively 10 and 1. So for example, here, this is a writing in Babylon. So this is their first digit, the second digit. In the second digit, they have 2 10s. Then each 10 represent a 60. So you have 20 times 60. In the second place, you have 10 and 2 1s, that comes 12. And the overall representation is 12, 12. So this is their system, very interesting. They can also use their fingers to represent numbers. So instead of using 1, 2, 3, they can use the 5 fingers here to represent, each of them represent one is 12. Then use this nachos here to count the numbers from 1 all the way to 12. So if I show here, it's 2, and it's going here, what is the number I'm representing? Can people see? Nobody got it?
You have to count. So 1, 2, no, 3. How it works?
Yeah, let's just get the convention and count from here. 1, 2, 3, 4, 5, 6, right? 6. This is 6. And this one is 12, it's 24.
Okay.
24 plus 6, 30. Very clever, interesting, huh? Now, something more for you. So what is number in the Babylonian system?
Okay, you need to go back. I don't remember it.
Okay, so this is a representation. This is 10, this is 1.
Okay. And this is 10, this is 1, so 3.
Yeah, look, there are three places. There are like, 3 different, digits. That means the first, second, third digit.
Okay. 1, 1, 1.
Yes. So officially it's 1, 1, 1. But if you translate into the decimal number, what it is? It's 1, 1, 1 in the sexagesimal representation. So this is one, just one, right? And this one is 60. This one is 3600. So this number is 111. It's 3661. Interesting, right? They can use a very small number to represent astronomical large number system. So not only the Babylonians, Egypt also compute the arithmetics in a different way. For example, here, if they calculate 5 times 6, what they do, they put some beans here. Some, I'm using this circle represent one kind of bean, and plus sign represent another kind of bean. So if they calculate 5 times 6, they start putting the first row with the 5 beans on the left and 1 bean on the right. Then they start filling from the right hand side row, right hand side of column, sorry, with a second block by putting 2 beans, the right hand. If they put 2 beans here, they have to fill this row with the corresponding number of the white beans. And then continuing on, it's 1, 2, 4. You see, this is 2 is double of 1, 4 is double of 2. Now, when you start calculating 5 times 6, and they start looking, the system is going backward so 6, 5, 4, 3, 2, 1. So this first row doesn't count. Then they remove the first row and arrive this final answer, which is just so much number of beans. It's equal to 5 times 6. So what's interesting about this calculation is they're actually using the binary system. If you look at the bean in the middle here, which I highlighted, this number is 6 in binary. So I just want to use this example to stimulate some interest about binary systems. You can also use your fingers to represent the number in that binary. If I use this, what is a number representing in binary system? So if I use this one, this is 0, this is 1, 2 states, 0, 1, 0, 1, because binary only have 0 and 1, right? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. If I use this one, I start from this, let's the first digit, second digit, third digit, what is the number? So this is 1, 1, 1, right? 1, 1, 1. 1, 1, 1 in binary is 7. So this is 7. Okay, let's get into some examples, bits and bytes. Bits, as I mentioned before, is like a bit 0 and 1 representation of systems. Bytes is a unit of 8 of them to come together based on arbitrary definition historically to represent one word, which consists of 8 bits. And this table, we're just happy to talk about this number system in GDAL. And we're going to go a little more details about the range of numbers and some interesting caveats. Okay, so I think the conversion of binary to decimal to you guys probably already familiar. If you have a decimal place, if you have a binary system to go into decimal, you basically just using this 2 to the power, multiply each individual digit starting from the 2 to the power 0. So shown here, here, you go at 10. If you go from decimal to binary, basically do the division. So you do the division and take remainder. And once you finish, you're going backwards, top down, you arrive at the binary, which is 1010. I think it's very simple. I will not dwell time on here. What is interesting is the presentation for binary point, which is floating. So this is basically summarize the entire computer system, how the data was stored. Let me just break down this for you. If you remember, before we have this system where we convert the binary into decimal, it's basically can be viewed as a addition of series numbers, and each term is representing as a fraction. Now, in this particular representation, we have several things. One is a sign, tells you this number is positive or negative. The other one is a base. If the binary is base equal to 2, if the decimal is base is equal to 10. If it's other bases, whatever number come here, become that particular base, we do the counting. Precision is this P. It tells you how many points you can have after the dot. That's in the decimal place. And this L and U represent the lower and upper boundage for this exponent. So the overall system can be used to represent all the numbers. But there's one key thing here you should pay attention, that this system has it's a discrete system. So based on definition, these numbers continuously, which I start from here, they are called mantissa. Then the fraction after the initial dots, this digit, it's called a fraction. And this sign, exponent, mantissa are stored separately in the computer system. If this first digit is always non-zero, it's called, this system is normalized. In the modern computer system, people normally use it, especially in the binary, because in that way you can save one more place. Now, this becomes important, the properties of this representation. As we all know, the floating point is a continuous, the real numbers is continuous, infinite sequence. But however, in the computer system, we cannot represent numbers continuously and infinitely. So instead, we have to use the finite and the discrete system to represent the numbers. And that creates some interesting and potentially funny or mistaken results. So let's just get a little bit understanding the basic setup of the system. So this is the thing, just go over again. We said how the number can be represented in the computer. Then with the setup of both lower, upper bound, precision, and base, one question to ask is how many numbers this particular representation can represent, right? So it should be such. Can anybody help me to explain this formula? Why is such? The first one is easy. The first one is 2 because you are plus minus, right? And second one, beta minus 1. Why is beta minus 1? Beta is the base, right? So this is representing the possibility of the first digit in the mantissa. So that's basically D0. How many possibilities for D0? And this part is a fraction. That's the possibility for fraction. And this for the exponent. And altogether, because they are represented in this way, they are independent. According to the rules of multiplication, this is total number of possibility representations this particular formula can represent. Then there's plus 1. I think we come to the most easiest part. Can somebody help me? Why is it plus 1? Okay, let's go back a little bit to look at the table. Maybe it's an interesting thing to see here. Look, if I look at this integer 16, right? It starts from minus something 768. And the maximum is 767. Why? Why it's not symmetric? Because you look at the formula we use, it's pretty much symmetric.
Because you have the 0.
Yeah.
In the center.
So much, yeah. It's 0 in the center. That's why you have 1 here. Then you can also calculate the lower bound and upper bound. And this is the number you can calculate to understand in the system how this number were arrived. Okay. I will just skip this part to get into the most interesting thing by using a toy example. So in this case, what I'm showing to you is importantly to recognize the number system in the computer. The space between them is not evenly distributed. So let's say I have a toy system with beta equal to 2, p equals 3 with the bound -1 + 1. Of course, 0 is always there in the center. then what is the immediate next number you can store in the system? So mathematically, it can be infinitely small. But in the computer, you cannot. What's the next immediate number you can store? Look at this formula here. Beta equal 2, p equals 3, and lower bound, upper bound is -1 plus 1. So when it's 0, that means all is point at 0, then this is 0. So that's the center point, right? Then the immediate next point is the number where you can populate in these parentheses, right? So this one has to be 1. Then the immediate next one is just a slightly larger than 0 will be the first decimal place, because all these are 0. I have only beta equals to 3. I have only 2 digits. So that means 1 over 2 squared. What's 2 squared? 4, right? 1 over 4. So that means 1 plus 1 over 4 is what?
1/4.
Yeah. It's 5 over 4, right? Then you start calculating this one. This is the beta to the power of lowest lower bound, it's -1. So that's 1 over 2. So when this is 0, when this is 1, this is 1 over 2, you get what? 1/2, right? This is this point, 1/2. The next one, when you have 1 over 4 here is it's a 1 digit up. It's a 5 over 8. It's 5 over 8. You see what's written here is 4 over 8, 5 over 8, 6 over 8, 7 over 8, and 8 over 8. And this space between 0 and 1/2 has nothing. This system cannot represent any number in this space. And that causes consequential result when you do the computation. So let's just go briefly to the real system where we talk about flow 32 and flow 64. The important here is the number of fractions for flow 32. You see they are stored differently, the sign, exponent, and fraction. The number of digits can be used to represent each part. It's fixed. In the case of flow 32, which is used a lot in the GDAL and the geocomputation, the precise representation for this system is maximum to the 23 digit in the fraction. That means the maximum number this system can represent precisely is going to be 2 to the power 24. What happens if you have to represent?
Longzhu, can you go back?
Sure.
So one question: the green part is representing the integer part.
Exponent.
Correct.
The green part is this one.
Green part represents the integer.
Yes.
I mean the integer. I mean big,
not
larger
integer.
than 0. No, larger than 0. Sorry.
The exponent. So the green part is exponent. This one is e.
Okay.
The first one is the sign. The second exponent. The third one is the fraction. It's not integer. It's exponent.
Okay.
So if you cannot represent the number precisely, you have to approximate. There are basically 2 ways of approximation. One is for the truncation, the other for the rounding. Truncation is pretty much, Giuseppe already showed example. If a float, you convert that one into integer, you just cut off whatever after this dot. In this example, I'm showing rounding in the first place, you just remove the last 2 digits. But if you round, you basically round the number based on rounding rules. And that causes the machine precision will be different due to the rounding action or the truncation action. As you see here, the machine precision for rounding is actually a little better than truncation, as you already know, based on this particular system. And this machine precision is also important. And this tells you how much space you can store between numbers. Now let's just get into a real life example. This is a case of code in Python. I think many of you will code this one. I just import the numpy, that's np, and put a range. Basically, I want to produce a sequence number from 0 to 1 with a space 0.1. And I want to make a judge to this sequence and set if this a particular instance going to be equal to 0.6. What do you expect? Anybody can help me? What do you expect if you see the expression there? It's a sequence from 0 to 1, right? With space 0.1. That means mathematically, it has to be a certain point. It should be equal to 0.2, isn't it? Does it make sense to everyone?
Yeah, to 0.1, 0.2, 0.3 until 0.6. So it should be something equal to 0.6.
Yes, thank you so much, Sapi. Then if you look at the result, if you are curious, you can run this in Python encoding on a machine. The result checking is always false. And this is a real life example. Another one. This is C language. I set up several floating points. I give a number here, which is x, y, and z. Then I just do some simple mathematical addition. This is the first print out is original. The second one is x plus y, and third one is x plus z. So the original one is this number, particular what it is. It's a little big. Then x plus 1 should be this number plus 1, right? And what do you see here?
Is it correct or not?
I think it's not correct mathematically, but it's correct computationally.
Anyone can say something. What is strange over there?
Yeah, anybody want to say something?
Yeah, actually, I just recently Googled that problem because sometimes if you just add numbers together in Python, it just gives you something that's like 35.99999 instead of 36. But yeah, I tried to understand, but I couldn't really grab why this is the case. And it's really annoying because you always have these huge numbers there instead of just a number as it is, like it's super, like an integer even. It just gives you something with a lot of decimal places.
Yeah, thank you so much for your input, Alex. So let me just finish first of all about this one. All these calculations, the result x plus y or x plus z are incorrect mathematically. If you see here, x plus 1 should be 16777,217, but this is incorrect. And plus 5, you're going to be end up with 21, and you end up 20. Also here is incorrect. Now, the answer to this one all lies in the representation of the floating points, which is the formula here. Because we cannot represent every number precisely in the computer system. It's a finite, discrete system. We have lower bound and upper bound, and we have machine precision. And this example, I think, is very good to show you, for some places, if you have to represent the number in computer, in this computer system, say 0.1, you cannot. The best you can do is to using 0.5 to approximate 0.1. And that is the result, that's the source of these odd arrows here. So I hope this part is entertaining. I will just finish off by saying thank you for your attention with a little joke. 10 people in the world that understand binary system and those don't understand. And in the end, there's some good references if you want to go further into this computer system. And also, I want to play a game with you. You can treat it as homework. I think probably won't have enough time in the classroom. The game is like this. So let's say you have 10,000 people standing in the queue, right? And they start announcing their positions. Of course, come from 1. The first person say 1, second person 2, third person 3. Then you start announcing. So once the announcement is finished, all those people who have got odd numbers will be removed from the queue. So those people who have got odd will out. The only one left are the even numbers. Then this remainder will reform the queue. For a smaller queue, then become the second round of announcement. Start from 1 again, 1, 2, 3, 4, 5. Again, the second time, the odd number will be eliminated. And the process repeats until the end. Only one person left in the game, who will be the winner. So now the question is, if you want to be the winner, which position should you hold? Should we talk about this right now, or we leave it for next time, Giuseppe? My talk is
okay.
finished.
Let the student think a bit. I think I know, but I will keep for me.
Yeah, it's very interesting. You know, for the end of class, just got a little brain honing.
Okay. Yeah, I think.
Say something. Raise a hand. Who says raising hand? You know something? Say something. Okay, I think we're gonna have 2 minutes left. If you want to have something to wrap up, Giuseppe, I think I'm happy to turn it over to you. I'll leave this one as a afternoon or later afternoon brain appetite. So we can talk about next time. That's all about me. Thank you so much for everyone's attention.
Yeah, thanks, Longzhu. Yes, really interesting talk. And I want to stress a bit, let me go in sharing again. For closing, I want to stress a bit. So these are very important, this number, to understand. So in particular, let's try to summarize in the real case where this number come from. Anyone can help me. So where the 255 is coming. Anyone? 2 to the power of 8. Okay. Yeah. To the power of 8, and then you have a shift to the 0, and then that's why it becomes 255. And the same is for the other one that I think is the 16. Okay. Yes, to the power of 16. So it's going to be this one, and then if you shift halfway to the 0 in the center, you have also a negative, and then you have 2 to the power of 32, like it's over here, to the 32, you get this number over here. So pay attention about the floating 32. So the floating 32 is to the power of 38. So be careful. You have a very to the power of 48. You have a really long digit, but these are the upper limit. Okay. So there is something really hidden in this computation that is coming from what Longzhu was explaining, that in other words, the float 32 is true that it's very long number. You have 38 places that you can fill it up, but the value higher than 2 to the power of 24 are not well represented. So in other words, if you store it integer number bigger than this number, okay, they are going to be wrong the computation. Okay, so in this kind of problem I raised up really when it was Longzhu like 3 months ago, that I was trying to do some operation, and I was trying to make a bit of inversion engineering to see if I was getting the number correct, and it's wrong. Why? Because that one is coming from the C code that Longzhu was expressing. So whenever you try to add it to in the C, and due to the GDAL info, the TIF are supported by a C number and limitation. So if you try to do in the float 32, you are trying to sum number bigger than this, is going to be wrong. You are going to receive a result, but it's going to be wrong. Like Longzhu says, it's computationally correct, but it's numerically wrong. So pay always attention on this. And in particular, I built up this nice exercise that is using GDAL. So tomorrow we are going next time we are going to progress in see the different application of GDAL and so on. But for the people that want to already go a bit further and start to play, all this kind of, let's say, mistake or imprecision, more than mistake, are summarized in this data type. So if you click in this study case, it's very funny. You get to this web page where we create a dummy raster file using this special format or ASCII file. Okay, so you have this. I use the AWK to create a matrix and then to convert it to a TIFF. And then we use these numbers, and then I want to just multiply. I just want to multiply this number by 22. Okay, so you can use GDAL calc, but you need to be careful to avoid these problems. Okay, because if not, your computation will be wrong. And then how you can check if they are correct calculated by, by transfer back your TIFF in a ASCII file and then print. Okay, so over here you can see the number if they're correct. So then you can do, okay, you can do by the calculator, you can do this times this multiple times 22, and you can see if you get this one. So this is correct, but you will see, you will have a bit of trouble to understand the GDAL calc, which one is how to build in order to have a correct answer. Because again, if you make a mistake, you will have an answer if it's not syntax error, but it will be wrong. So this is a good exercise to play with a little matrix, and it's also very good to understand how you create a TIFF from a matrix, and to understanding quite well this process. And tomorrow next time we will go through all the GDAL application. But for people that you already use GDAL and GDAL calc, they can already understanding that you can do in the laptop over here, just copy paste and in a script, and you can do it.
Hey, Giuseppe.
Yes,
the
please.
black square appear again. Maybe you better next time try to go over this part again.
Is already still there?
Yeah, it's here.
Sorry.
Right now it's gone.
Okay. Maybe when I select, maybe it's when I select. Okay. Okay, so feel free to spend a little time and also to read in internet about this problem of precision, because when you start to play with big number, it's coming up along this problem. Okay, so any question or doubt is also good this time if you want feedback or something. Okay, I think everybody's.
I have a small question, but it's not about all of this. It's just because you presented function about GDAL and OGA at the start. And I was wondering, I've been looking for a function, I don't know, maybe it's not there yet, but like to intersect between shapefile and raster. I had to do like a quite heavy intersect function where I would like have, let's say, raster with don't cover on one side, and then a grid. And in every grid cell, I wanted to have like the proportion of land cover. And I couldn't find a good function that could do the job.
Okay, so this one was covered and is a very similar task that Julia was doing. Okay, so
okay.
summary statistic inside to the between a
so
vector
actually,
and raster, yes, and I posted in the Slack. So start to play with that one.
So that's actually PK tools that I should go for.
Yes, so the PK extract OGR is going to do this kind of zonal statistic or regional statistic. Yes, yeah. Very good.
Thanks.
Okay. Any other question in this direction? Okay. So please start to play as much as possible we are not giving, we are not grading or giving assignment that, but start to use as much as possible, because then when we will enter in the machine learning algorithm implementation, all this stuff will be, like you need to do it. So we'll try to get familiar with the tools, implementing your routines, and will come in automatically all the rest. Okay, that's it for today. We will resume next week.